In this fascinating deep dive, we explore the profound question of what makes something real. Inspired by a simple yet profound query from an 8-year-old child, the video delves into the debate between matter-first materialism and mind-first operationalism. Through the Spectral Observer Framework, SOF, we examine how the interaction between fundamental laws L, observer probes P, and resources shapes our perception of reality. This comprehensive analysis bridges the gap between physics, biology, information theory, and philosophy, illustrating how our understanding of existence is constrained by the resources available to our brains, bodies, and technologies. Join us as we unravel how matter, mind, and resources come together to define the reality we experience.
Have you ever truly stopped to wonder, like at a really fundamental level, what makes something real? It's one of those questions, isn't it? It sounds like it belongs in, I don't know, philosophy class or maybe whispered late at night somewhere.
Right, seems abstract.
But it's way more profound than that. Actually, the spark for this whole deep dive came from an 8-year-old child, believe it or not.
An 8-year-old?
Yes. Yeah. Apparently, he interrupted this really serious academic debate, the classic matter versus mind thing.
Oh, that old chestnut.
Exactly. And he just comes out with this, disarmingly simple question. He said, "Excuse me, before you fight about matter or mind, tell me, what makes you sure that something exists at all? What is it that says this is real?"
Wow. That would stop you in your tracks, wouldn't it?
Totally. Silence in the room, apparently.
Yeah, because that simple question, with that kind of, innocent clarity, it forces everyone, physicists, philosophers, biologists, everyone to just pause.
Yeah.
It cuts right through all the complex arguments we build up over centuries.
So what's the usual answer? The grown-up answer?
Well, the initial sort of standard scientific answer we often give is that existence boils down to detectable redundancy.
Detectable redundancy. Okay, what does that mean in plain English?
It means if something leaves a mark, a trace, that's consistent, that's repeatable across different observers or different tests. If it keeps showing up reliably, independently,
then we start to count it as real.
Exactly. It's about reliability, consistency, and observation. Doesn't matter who's looking or what instrument you're using. If it's consistently detectable, we say, okay, this thing exists.
Right. And that idea, that core concept, is exactly what we're diving into today. It's this fascinating field, kind of at the intersection of physics and information theory, maybe even philosophy.
Right.
Resource-constrained physics of reality. We're going to take that profound question, that child's question, and explore it not just philosophically, but using this really powerful analytical tool. It's called the Spectral Observer Framework, or SOF for short.
Right, the SOF.
Yeah, and this framework, it lets us translate that kind of childlike wonder into something rigorous, something scientific. It gives us a formal operational definition of existence, for the grown-ups, the mathy crowd maybe.
It really does. The SOF helps us break down this big fuzzy question of what's real into measurable, definable pieces.
Okay, so how does it work? What are the pieces?
Okay, imagine the universe itself, right? All its underlying stuff and rules. That's the system.
The system, got it.
In the SOF, we model this fundamental reality mathematically as something called a linear operator L.
Oh, okay.
Think of L like the fundamental score of the universe's music, the unchanging rules, the grammar. It dictates what's possible.
It's sheet music.
Exactly, the sheet music. Now, any sheet music has underlying notes, harmonies, right, for our spectrum. For the system L, these are its eigenvalues.
Eigenvalues. Heard that term before.
Right. These eigenvalues are considered the truly objective, unchanging fingerprints of matter. They're independent of anyone listening or observing. They're the inherent properties, the bedrock of what is.
Okay, so that's the universe itself, L, with its fundamental fingerprints, the eigenvalues. But then there's us, right? Or anything looking at it.
Precisely. That brings us to the second piece, the observer.
Okay.
And the observer could be anything. It could be you, me, a sensitive scientific instrument like a microscope, or even a biological organism, a bat using sonar, an ant colony sensing its environment.
So anything that interacts with the system.
Exactly. We represent the observer mathematically as a probe matrix P.
P for probe. Makes sense.
And P isn't just what you're looking at. It captures how you're looking at it. Think of it as your specific instrument, your microphone or camera. Is it high fidelity? Is it noisy?
Ah, right, because real-world observation isn't perfect.
Never. And that's crucial. This probe P always operates under real-world constraints. There's always some background noise. There are energy budgets. You can't spend infinite energy observing. And there's finite bandwidth. You can only process so much information per second.
So it's not just about the thing L that is, but also about the probe P that's seeing it and all its limitations, noise, energy, bandwidth.
Exactly. They're intertwined. And that leads to the third crucial component, information flow.
Okay, how much information actually gets from the system to the observer?
Precisely. We need a way to measure how much useful information about the system, L or its state U, actually makes it through the observation process to the observer's measurement.
How do we measure that?
We use a concept from information theory called mutual information, usually written as IUA.
IUA?
Okay, think of mutual information as a precise way to quantify how much knowing the measurement Y tells you about the original system state U. It measures the reduction in uncertainty.
So how much does the observation actually help you pin down what's going on in the system?
Exactly. More broadly, we can talk about channel capacity C. That's the maximum rate at which information can be reliably transmitted from the system to the observer through this channel, defined by the probe, P, and the noise.
Okay, like the maximum data speed of your connection to reality.
That's a great analogy. This I or C literally tells us how many clear, distinct pieces of information, how many bits about the system an observer can reliably pull out, given their probe and the noise.
And this is where we get to the punchline, right? The
Yes.
formal definition of existence within this whole SOF framework.
Yes, this is where it all ties together beautifully. The formal definition of existence in the SOF is actually remarkably intuitive once you have the pieces.
Lay it on us.
Okay.
Mhm.
A feature S of the system that could be a specific property, like is particle A present, or a pattern, or even a whole subspace of the system's possible states exists for an observer with probe P if the mutual information between that feature S and the observer's measurements Y, so ISY, is greater than or equal to some small positive number, epsilon.
ISY. So the information you get about the feature has to be above some minimum threshold.
Exactly. F represents a minimal reliability threshold.
Hmm.
It means the feature has to be detectable above the background noise and with enough consistency to be meaningful.
It can't just be a random fluctuation, a fleeting blip that might be noise.
Precisely. It has to pass that reliability test. Your observation has to genuinely reduce your uncertainty about whether S is present or not by at least F.
And this mutual information test is powerful.
Incredibly powerful. It captures any kind of statistical dependence, linear, nonlinear, complex patterns. It doesn't care how the feature is encoded, only that information about it gets through reliably. And like I said, it connects directly to channel capacity C. It tells you how many bits you can get about S.
Is there another way to think about it?
Yeah, there's an equivalent way called the observable subspace test. It sounds a bit more technical, but the idea is similar.
Okay.
It says that for a feature S to exist, for an observer P, its observable energy for that probe must be large enough. We write this as EPS equals PF2.
Whoa, okay. Breakdown.
PSS, pi of S, is a projector. It mathematically picks out the part of the system corresponding to feature S. P is your probe. So PS basically asks, how much does my probe P interact with, or C, the feature S?
Okay.
And the dot F2 is the squared Frobenius norm, essentially. It measures the strength or energy of that interaction.
Yeah.
So the test says this interaction strength, EPS, has to be large enough for you to reliably test hypotheses about S.
So your probe has to light up significantly when the feature is there.
Exactly. It connects directly to this idea of spectral redundancy. If S corresponds to, say, a degenerate eigenspace, multiple states with the same energy, AS projects onto that whole space. The test checks if your probe P couples strongly enough to that entire subspace to make reliable measurements about it.
That's a fascinatingly rigorous way to frame what's real. It's not just about being there fundamentally, like Elle says.
Yeah.
It's about being detectable, leaving a consistent, measurable trace for an observer with specific capabilities and limitations like P and A.
Precisely. It's operational.
It's like saying, that hidden object in the room only truly exists for you if your flashlight P is strong enough, EPS, and your eyes are sharp enough to distinguish it from the shadows noise.
That's a perfect analogy.
Okay. So with this incredibly powerful framework, the SOF, in hand, now we're ready. We can finally dive into one of humanity's oldest, deepest, and often most heated debates, the classic showdown, matter first versus mind first.
The great debate.
Exactly. And this isn't just some abstract argument for dusty philosophy books. As we'll see, it has profound implications for how you understand the very fabric of the universe you live in and your place within it. It gets really interesting here.
All right, let's start by laying out the case for the matter-first perspective, also known as materialism or physicalism.
Okay, the materialists. What's
Yeah.
their core claim?
It's pretty straightforward, actually. Their core claim is reality is what truly persists, objectively, independent of any observer, independent of who looks or how they look.
It just is.
It just is. They argue that the fundamental properties of the system, L, are the bedrock. Things like its eigenvalues, those objective fingerprints we talked about, conserved quantities like energy or momentum, other mathematical invariants. These are the non-negotiables of reality.
The fundamental constants and laws.
Exactly. And from their viewpoint, if you just gather enough data, use enough different kinds of probes, with sufficient precision, a low noise, high budget M, then the true underlying reality, the system L itself, is inevitably uniquely reconstructible.
So observer limitations are just temporary problems.
They see them as practical hurdles, yes. Not fundamental barriers to knowing the objective truth. In the end, for them, matter dictates. Full stop. Mind or observation just reveals what's already there.
And they have some pretty strong arguments for this, right, using the SOF language.
Oh, absolutely. Their arguments are compelling. Let's take their first major point. The spectrum as an invariant catastrophe.
Okay, sounds dramatic.
It kind of is. The raw spectrum of L, those eigenvalues, is considered absolutely observer independent. It's not up for interpretation, it's just a mathematical property of the system itself. Like the mass of an electron, it just is.
Fixed, immutable.
Right. And crucially, many macroscopic laws think about things like how waves propagate, dispersion relations, or the conditions under which a system becomes unstable. These are often fixed mathematical functions of this underlying spectrum, like calculating moments, TR, LK.
So the big picture rules depend directly on these fundamental notes.
Exactly. So the materialist argues, even if different observers use different coordinate systems, different conceptual frameworks, maybe even different geometries to describe the world, they must ultimately agree on a whole rich set of constraints and macroscopic laws that are dictated solely by that invariant spectrum. It's like saying no matter what language you use to count 2 + 2 = 4, the underlying arithmetic, the spectrum, is fixed.
That's a strong point. You can't just invent new physics without changing the fundamental spectrum.
That's the materialist punch.
Yeah.
The spectrum provides hard, objective constraints. But, and here comes the rebuttal from the mind-first side.
The counter-argument.
It's a sharp one and really gets to the heart of the SOF.
Yeah.
They say, yes, okay, the full spectrum of L might be invariant in theory, but observers in the real world, with real probes P, they almost never measure the full spectrum.
We can't see everything.
Exactly. Think of it like trying to understand a symphony by listening through a tiny, crackly phone speaker. You're limited by noise, by the coarse graining of your sensors. They aren't infinitely precise. Maybe you just don't have enough time or energy to measure everything.
So we only get a partial picture.
Always a partial picture. We only ever probe a subset of those objective invariants. And here's the crucial insight. This limited view means that two different observers, P1 and P2, looking at the exact same underlying system L, can legitimately infer completely different effective laws for that reality. These laws might even seem contradictory at first glance.
How can that be?
Because each observer's effective law is perfectly consistent with the very small sliver of the objective truth, the partial spectrum, that they manage to reliably detect above their noise threshold.
Wow. So my perceived laws depend on what I can actually measure.
Precisely.
Yeah.
It highlights how the laws of physics we discover aren't just passively waiting out there. They are actively shaped, co-created by what we can detect given our very real resource constraints.
And that's a profound challenge. Okay, what's the next materialist argument?
They often bring up universality and the renormalization group, RG.
RG sounds familiar from physics.
Right. The idea here is that many macroscopic phenomena are surprisingly insensitive to the tiny microscopic details.
Like how water flows. Doesn't really matter about individual H2O molecules vibrating. You just use fluid dynamics.
Exactly. Perfect example. Water behaves like a continuous fluid, obeying something like the Navier-Stokes equations, regardless of the messy quantum stuff happening at the micro level. The materialist argument is you can zoom out, average over the micro details, and certain universal large-scale emergent laws remain incredibly robust.
And different observers should find these same universal laws.
That's the claim. Different probes, even if they measure slightly different microscopic aspects, should still recover the same universal PDE, like the diffusion equation or a wave equation, or the same scaling laws near a phase transition. These large-scale laws seem robust. They don't seem to care about the observer's specific probe details.
Okay, seems solid. What's the mind first rebuttal?
It's subtle but important. They argue that universality, while a powerful concept, is often asymptotic. It holds perfectly only in theoretical limits, like infinitely large systems or zero noise, or infinitely long observation times.
Which we never have in reality.
Never. So they argue, if an observer's specific probe selection P, or way they choose to coarse-grain the data, happens to change which underlying operators in L are relevant to their specific measurement. Especially if the system has degeneracies, multiple states with the same eigenvalue, then the RG flows, the mathematical process of zooming out, can actually diverge. Meaning that at finite scales, the scales where all real-world observations happen, universality might not be guaranteed. What appears universal to one observer, P1, might actually look different or follow a different effective law for another observer, P2, because their probes pick out different relevant features in that degenerate landscape. Universality isn't always the inevitable outcome for resource-constrained observers.
Okay, so the way you look can influence even these supposedly universal laws. Tricky. What else do the materialists argue?
A core tenet for them is reconstructability with sufficiently rich probes.
Meaning, if you just observe enough, you'll get the true picture.
Exactly. They maintain that if you have enough different observations, enough variety in your probes to measure everything from every angle, every possible interaction, then the true underlying system L can eventually be reconstructed perfectly, uniquely.
And any apparent freedom or observer dependence?
It's just an artifact of limited information.
Yeah.
It's because your P wasn't rich enough or you didn't collect enough data. Just keep measuring, they say. Keep improving your probes, reduce the noise, and the single objective truth L will inevitably, unequivocally emerge. Mind's apparent freedom is just lack of data.
Seems logical. What's the catch?
The catch, according to the mind first side, lies again in those pesky degenerate subspaces.
Where multiple states have the same eigenvalue, right?
Right. In these subspaces, even if you have complete observability of all the algebraic invariants, like the eigenvalues themselves, there's often an intrinsic gauge freedom. The specific basis you choose to describe the states within that degenerate subspace is fundamentally non-identifiable from the invariants alone.
Like choosing coordinates. Yeah.
Kind of. Imagine a perfectly uniform sphere. You know its radius, that's an invariant, but which direction is north? There's no unique north pole defined by the sphere itself. You have to arbitrarily choose one.
Ah, I see.
Similarly, in these degenerate subspaces, even if you can measure all the eigenvalues perfectly, there might be inherent ambiguity in how you describe the actual states, like coherent superpositions or relative phases. The observer's choice of measurement basis P effectively resolves this ambiguity. So even with theoretically complete information about invariance, there might still be an observer-dependent choice in the description.
So perfect reconstruction isn't guaranteed even in principle if degeneracy exists.
That's the mind first claim. The observer's probe P inevitably selects a particular description from potentially many equivalent ones within that degenerate subspace.
Interesting. Okay, next materialist point.
They heavily emphasize how spectral constraints enforce conservation laws.
Like conservation of energy, momentum, charge.
Exactly. They argue that fundamental symmetries in the system operator L, mathematical properties like L, commuting with some symmetry operator S, directly imply observer-independent conservation laws. Narrowest theorem, basically.
Right. Symmetries lead to conserved quantities.
And these conserved quantities, they argue, are hard objective constraints. They put absolute limits on what kinds of effective dynamics any observer P can possibly infer. You simply cannot conjure up an effective theory that violates conservation of energy, for example, if the underlying L has time translation symmetry.
You can't break fundamental laws just by looking differently. Seems obvious.
It does seem obvious. Yet the mind-first perspective offers a counter. Observers can, in effect, break apparent symmetries through their specific coupling P and coarse graining.
Ow.
Think about it. A global conservation law, like the total energy of the entire universe, might be absolutely true according to L. But if an observer P only measures, say, local temperature fluctuations in one tiny corner of the room, their limited scope and the way they average or filter the data, coarse graining, might lead them to infer different effective conservation laws that only hold locally or approximately. They might see energy seemingly appearing or disappearing in their little patch, even if it's conserved globally.
So the perceived conservation laws can be observer-dependent.
Yes, depending on the scale and nature of the probe P. The underlying conservation dictated by L is still there, but the effective continuity equations or conservation laws an observer actually uses and finds useful might be different, shaped by their interaction.
Okay, that's subtle. Last big one for the materialists.
Prediction and counterfactual control is a powerful practical argument.
If you know the rules, you can predict the future and control things.
Precisely. The core idea is, once you know the true material operator L, the fundamental rules, you gain the power to predict how the system will behave under any conditions, even conditions you haven't directly observed, counterfactuals. And crucially, you can manipulate or control the system in predictable, repeatable ways that work regardless of who is doing the controlling.
And this power is objective proof of the law.
For materialists, yes. This robust, observer-independent predictive and manipulative power is the ultimate practical litmus test for a true, objective physical law derived from L. If your theory allows this, it reflects reality.
Makes sense. You can build bridges based on physics, and they stand up whoever builds them.
Right. But again, the mind-first rebuttal comes back to those degenerate systems. They point out that, perhaps surprisingly, predictive power itself can become observer-relative in highly degenerate systems.
How so?
If different types of probes P interact differently with the various states within a degenerate subspace, maybe one probe excites mode A, while another excites mode B, even though A and B have the same energy, then they might create different effective control actions. Trying to control the system using probe P1 might lead to different outcomes and require different predictive models than using probe P2. Your ability to predict and control becomes tied to your specific probe P, not just the underlying L.
So even prediction isn't purely objective in these cases.
In these degenerate cases, the mind-first side argues it becomes observer-relative, dependent on the specific interaction channel P.
Okay, wow. So that's the matter-first case laid out. Reality is objective, L is king, and observers just need better tools to see it clearly. Powerful arguments, but with some really intriguing counterpoints.
Definitely.
So now let's flip the coin. Let's hear from the mind-first perspective, sometimes called idealist, or maybe more accurately here, operationalist.
Right.
Their core claim challenges the materialists head-on, right? They say not so fast.
Exactly. For them, reality isn't some fixed, metaphysical, absolute waiting to be discovered. It's fundamentally operational. It's defined by what can be measured and interacted with by an observer P with finite resources.
So the observer isn't just passive.
Far from it. They argue that the very way an observer probes the universe, P, actively shapes what they perceive as real, what laws they discover, with finite probes, finite energy, finite time.
The real-world constraints.
Yes. They argue that the inherent redundancy and degeneracy within many systems, L, mean that the laws we discover are often not unique. They aren't universally given. For them, in a crucial sense, the mind selects. Or maybe better, the probe selects.
Okay, let's get into their specific arguments. What's the first big one?
One of their most fascinating claims centers on information geometry. Fisher geometry can be non-trivially curved even when the spectrum is fixed.
Fisher geometry. Fisher-Rao metric.
It sounds complex. It is a bit mathematical, but the concept is amazing. Correct. Imagine, again, the underlying reality L and its fixed spectrum as a perfectly flat, featureless landscape.
Okay, the objective base layer.
Right. Now imagine an observer P moving across this landscape. The Fisher-Rao metric, GAB, basically measures how distinguishable nearby points, parameter values, are from the perspective of this observer. It depends on the probe P and how it couples to the system.
So it's about the observer's ability to tell things apart.
Exactly. And here's the kicker. Even if the underlying landscape, L spectrum, is perfectly flat and unchanging, the observer's information landscape, described by this Fisher metric, can be curved.
How? Just because of the probe?
Yes. Purely due to the observer's choices, how their probe P couples to the system, how they might weigh different pieces of information, like coupling weights. This perceived curvature can arise solely from the observer's interaction.
What does curvature mean here, practically?
It implies that the observer perceives fundamentally different effective forces or equations of motion governing how things change in their perceived reality. It's like putting on distorting glasses. The flat ground might suddenly appear to have hills and valleys curvature, just because of the glasses, the probe P, even though the ground itself is unchanged.
So two observers, P1, P2, looking at the exact same flat reality, L, could perceive totally different forces and dynamics just because their glasses are different.
That's the claim. It seriously challenges our intuition about objective laws. It suggests that the forces we feel or measure might be, in part, artifacts of our specific way of sensing.
Mind-bending. What's the materialist rebuttal to that?
They'd concede the geometry can be influenced by the probe, but argue it's not arbitrary. They'd say this perceived geometry gap is still fundamentally constrained by the underlying spectral invariance of L. You can't just create any curvature profile you want. The objective reality still imposes hard limits.
Okay, it's constrained, but still potentially observer-dependent. Next mind-first argument.
This leads directly to the perhaps even more dramatic claim, the constructibility of incompatible effective laws.
You mentioned this before. One observer sees diffusion, another sees waves from the same system.
Exactly that. The claim is you can theoretically design two perfectly legitimate probe families, PA and PB, that interact with the same underlying system, L, but the effective dynamics they infer are fundamentally incompatible.
Like mathematically contradictory.
They might be described by entirely different types of equations. Observer A, using probe PA, might conclude the system follows a diffusion equation. Things just spread out. Observer B, using PB, might conclude it follows a wave equation. Things oscillate and propagate.
And both are right, from their perspective.
Both descriptions could be perfectly valid, self-consistent, reduced models of reality for their respective observers, given their specific probes and the information they extract. Yes, why? But these models aren't easily reconciled into a single unified description without considering the probes themselves.
That really hits hard at the idea of a single objective reality. What's the materialist counter?
They argue this apparent incompatibility is usually an artifact of limited perspective or incomplete information.
The not enough data argument again.
Right. They'd say if observers A and B pulled their data, shared information, or maybe designed a new probe PC that combined aspects of PA and PB, cross-coupling.
Then the incompatibility would dissolve.
Often, yes. The divergence, they suggest, arises from the restricted, incomplete nature of the individual probes, PA, PB, not from some fundamental metaphysical split where the system is both diffusing and oscillating. The full underlying reality L, if accessible, would resolve the apparent contradiction.
Okay, so it might be a matter of scale or completeness of observation. What about those degenerate subspaces again?
Yes, the mind-first side heavily utilizes operational non-uniqueness in degenerate subspaces.
Remind us, multiple states, same energy eigenvalue.
Exactly. The argument here is that within these subspaces, even if you know the eigenvalue perfectly, the observer's choice of measurement basis, how their probe P is oriented within that subspace, effectively selects which observables appear fundamental.
So the observer picks what properties seem real within that ambiguity.
In a sense, yes. Different choices of measurement basis P can lead to different observed effective theories, different apparent symmetries or broken symmetries, all consistent with the same underlying eigenvalue. There's an inherent ambiguity that the observer resolves, operationally, by the very act of measurement with a specific probe P.
So the observer's choice has real consequences for the perceived physics.
That's the claim. What's the materialist counter here?
They usually argue that while this mathematical freedom might exist in the abstract, physical probes rarely access it arbitrarily, meaning
Real probes P tend to couple to specific physical observables like position, momentum, spin component in a certain direction, rather than abstract mathematical basis vectors. This physical coupling, they argue, often breaks that residual gauge freedom automatically. It selects a preferred physical basis dictated by the interaction itself.
so the theoretical freedom might not translate into truly different realities in practice.
That's the materialist view. The interaction physics itself often resolves the ambiguity, making the observer's choice less ontologically significant than the mind-first side suggests.
Okay. Is there experimental evidence for the mind-first view here?
Yes, quite compellingly, in the form of experimental construct. Programmable observers generate different PDEs.
This isn't just theory. We can build systems like this.
Absolutely. It's been demonstrated beautifully in engineered systems, particularly metamaterials.
What are those?
They're artificial materials designed with specific, often unusual structural properties at the micro or nanoscale, which gives them exotic macroscopic behaviors like negative refractive index.
Okay.
Researchers have shown that by simply changing the observer specifically, how you place sensors and actuators to interact with and measure these materials, you can make the same metamaterial behave according to fundamentally different effective continuum equations.
Like the diffusion versus wave example.
Exactly. One sensor actuator setup, P1, might make the material's response best described by a diffusion equation. Change the setup, P2, interact differently, and the exact same physical material, L is unchanged, might now behave as if it follows a wave equation.
That seems like strong evidence for the observer shaping the perceived law.
It is very suggestive. The underlying microstructure L is constant, but the macroscopic law perceived by the observer P shifts dramatically based on the interaction.
What's the materialist response to these experiments? It seems hard to argue with.
Their response is crucial. They'd argue that these different effective operators, these lefts that depend on P, are only valid descriptions under the constraints of those specific observables. Meaning, the diffusion equation only works if you're only measuring the things P1 measures. The wave equation only works if you're measuring what P2 measures. The full underlying operator L still governs the system in its entirety, encompassing all possibilities.
So the lefts are just accurate but limited approximations.
That's their take. They're useful, effective theories for specific observational contexts, but they don't represent a true split in the fundamental reality L. They don't negate the existence of the underlying unifying L.
Okay, still holding the line for objective reality. One last argument for mind first.
It often rests on information-theoretic indistinguishability, sometimes framed using bounds like the Fano bound, leading to what they might call ontological opacity.
Breakdown.
The core idea is real systems, L, often have enormous redundancy, vast numbers of microscopic states that look very similar macroscopically. And real observers have limited resources, M.
Can't measure everything perfectly.
Right. The Fano bound and similar results tell us there's a limit to how well you can distinguish between different underlying states based on noisy, limited measurements. It becomes practically, and sometimes even fundamentally, impossible to tell apart myriad different microstates.
So we have to lump things together.
Exactly. The mind-first view here is that the laws we perceive, the reality we construct, aren't derived from precisely knowing the individual microscopic state. Instead, they emerge from these equivalence classes of indistinguishable states. Our perceived reality is built upon what is indistinguishable given our observational limits, P.
So the laws we see are laws governing the coarse-grained categories, not the true micro-details.
That's the idea. The limits of our perception actively create the categories upon which our laws are built.
And the materialist rebuttal.
They argue this is fundamentally a practical epistemic limitation about what we can know, not a metaphysical ontological one about what truly exists.
It's about our limitations, not reality's nature.
Yes. They'd say, sure, distinguishing states is hard now. But if we just keep increasing our experimental care, build better probes, P, reduce noise, take more measurements, increase M, maybe use quantum tricks, we can, in principle, keep collapsing that error, keep refining our distinctions. Mind's power here, they argue, is practical and about knowledge, not fundamental to existence itself. The underlying distinctions in L are still there, even if we can't currently resolve them.
Wow, what a clash. You can really feel the tension, can't you? Both sides using the same basic framework, L, P, I, AI, but emphasizing totally different aspects. Matter first focusing on the ideal limit of perfect L, mind first focusing on the reality of finite P.
It's a profound disagreement about where reality truly resides.
It really feels like both are right somehow. Like they're describing different sides of the same coin or maybe different regimes depending on the observer's resource.
You've hit the nail on the head. If we're feeling lost in this philosophical tug of war, who told me steps in? Who's the referee?
The math, the framework itself.
Exactly. The mathematics of the SOF acts as the impartial referee, providing the unifying synthesis. So the mathematics of the Spectral Observer Framework steps in. And its verdict is actually remarkably clear and elegant. It basically says both the materialist, L-focused, and the idealist, operationalist, P-focused perspectives are correct, but within specific domains.
Domains defined by what?
Defined by resources. It all comes down to the observer's capabilities.
Okay, explain.
With idealized, essentially unlimited resources, think infinite measurement time, zero noise, perfect sensors, P can resolve everything, infinite energy and bandwidth, then the mathematics shows the underlying system L is fully and uniquely reconstructible.
So in that perfect theoretical world,
matter wins, unequivocally. The underlying physical laws encoded in L are uniquely determined, objectively knowable, and universally accessible to any such idealized observer.
But that's not the real world, is it?
Not at all. That's the crucial distinction. In the real world, the world we actually inhabit, observers always have finite resources. Noise is never zero. Probes, P, are always bounded in their resolution and scope. Energy, M, and bandwidth, C, are always limited.
And under those conditions?
Under those practical conditions, the math shows that irrecoverability often reigns. You cannot uniquely reconstruct L. And in that domain, the mind, or perhaps better, the observer-specific probe P and its constraints, wins.
So the effective reality, the laws the observer finds, is shaped by their limits.
Yes, it's intrinsically shaped by their capabilities and limitations. P. Empty must bench. It's a conditional victory for mind probe, conditional on resource limits.
This duality, this switch between matter winning in the ideal and mind probe winning in the practical, can we quantify it?
Beautifully. It's captured formally in what's called the trade-off theorem.
Okay.
It's a mathematical inequality that relates the probability of making an error in reliably identifying some feature of the system, pair to the resources available. It generally looks like pair, FAMSN.
So the error probability depends on, M is the sensor budget.
Right. Number of sensors, energy, time, your total measurement effort. Is the noise level.
Yeah.
R represents the redundancy or degeneracy in the system's spectrum L. How much intrinsic ambiguity is there?
So more resources, less noise, maybe less redundancy, means lower error.
Exactly. But crucially, if resources are finite and noise is present, the error pair is always bounded above zero. You can never achieve perfect certainty in the practical world. This theorem sets quantifiable, measurable limits on what can be known and how reliably, given your resources.
It's not just philosophy, it's a measurable trade-off. And you mentioned a phase diagram.
Yes, this trade-off creates a fascinating phase diagram. Imagine plotting, say, your effective signal-to-noise ratio, which depends on M and S on one axis, and maybe the complexity or richness of your probes P on the other axis, related to M.
Okay, a map of possibilities.
This map clearly shows two distinct regimes, like phases of matter, solid, liquid, gas.
What are the phases?
In one region, typically where you have high SNR and rich probes, lots of resources, you're in the matter-dominant regime. Here, unique reconstruction of the underlying L, or at least its relevant features, is mathematically possible, or error is very low. Objective reality rules.
In the other region.
Cross a certain threshold, maybe your SNR drops too low, or your sensor budget M runs out, or the system's redundancy R is too high, and you enter the mind-dominant regime. Here, error for distinguishing underlying states becomes large. Multiple different effective realities, different simplified models or laws can be legitimately perceived and described for the exact same underlying system L, depending on the specifics of the probe P.
So the phase boundary depends on resources.
Absolutely. Where you sit on this phase diagram is determined by your resources.
This leads to the grand synthesis, doesn't it? The core idea of resource-constrained ontology.
Exactly. It's not about picking sides anymore. It's a deeper understanding that integrates both. Think of it like this. Matter, L, sets the hard constraints. It provides the ultimate blueprint, the fundamental rules, the possible states, the invariant spectrum. It defines the boundaries of the playing field.
It tells you what could be.
Precisely. Then mind, or probe P, selects an effective description. It paints the picture within those boundaries. It carves out a specific information geometry, focuses on certain features, builds simplified models based on what it can reliably detect.
It chooses what to see.
Within the limit.
Yes.
Yeah.
But critically, and this is the key insight, it's resources that decide the victor. The amount of energy, the number and quality of sensors, the available bandwidth, the noise floor. These practical limitations determine which perspective, matter first, focus on L, or mind first, focus on P, truly prevails in defining what is real for that observer in that context.
So it's not a compromise, it's resource-constrained ontology. The very nature of what exists for an observer is determined by and constrained by their available resources. Reality isn't just L, and it isn't just P's free creation. It's the result of P interacting with L under the constraints of M and P.
So going back to that 8-year-old's question, what makes you sure something exists? What's the synthesized answer now?
Well, fundamentally, both sides, matter and mind, actually agree on the operational core, detectable redundancy. Something exists for an observer if it leaves a consistent, statistically significant trace that could be picked up, ISY, given their specific probes and noise level.
Okay, detectability is key for both, so where's the difference?
The difference boils down to perspective and emphasis. Do you define ultimate reality by the theoretical idealized limit of infinite sensing where L is perfectly revealed? That's the matter-first metaphysical standard. Or do you define reality operationally, based on practical detectability? Do you accept that the inherent limits of real-world observation, PMC, are ontologically decisive in shaping the effective reality an observer actually experiences? That's the mind and matter co-creation view, the resource-constrained ontology view.
And the math supports this dual view.
Absolutely. It's perfectly summarized by the master theorem of this framework, in essence.
Okay, the master theorem states.
If channel capacity Cmax is infinite, representing those idealized conditions, then the fundamental system operator L is fully identifiable. Matter determines a unique objective law. Game over. Matter wins.
Great.
But if Cmax is finite, as it always is for any practical observer, any biological organism, any real instrument, then the theorem shows that observer-dependent effective laws, left depending on P, not only exist but are mathematically robust and stable. They are genuinely different ways of describing the system, tailored to the observer's probe P, yet entirely consistent with the underlying constraints of L.
This is why a bat sees sound echoes and we see light.
Exactly. Both are valid resource-constrained realities derived from the same underlying physical universe, L, but filtered and shaped by unique probes, P-bat, human, operating under different resource constraints. Neither is wrong. They are different operational realities.
That's a huge shift. Reality isn't just one thing. It's this dynamic interplay between the world and our limited way of accessing it.
It's objective in its constraints, L, but potentially subjective or observer-dependent in its manifestation.
Okay, this is fascinating theoretically, but what does it all mean in practice? Especially for us, for living organisms. This can't just be abstract physics, right? This must be fundamental to biology.
Oh, absolutely. You could argue that biology is the ultimate case study for resource-constrained ontology. For living organisms, this isn't philosophy, it's life and death. It's the very foundation of how we perceive, interact with, and survive in our world.
So our biological reality is a resource-constrained reality.
Inherently. The core claim here is that which layer of reality dominates an organism's perception. The raw physics, L, or a more filtered effective layer, left P, is decided by a constant ongoing process of optimization.
Optimization of what?
Optimization of fitness-weighted information per resource cost, playing out across all relevant timescales.
Okay, break that down. Fitness-weighted information per resource cost.
Think of it as life's fundamental economic problem. An organism is constantly trying to maximize its expected utility or fitness based on the actions, A, it takes in its environment. But taking good actions requires information, which requires sensing, P, and sensing costs resources,
Yeah,
C.
energy, time, building the sensors.
Exactly. So the organism faces this optimization problem. Maximize EUAX, C a P. Maximize expected utility minus the resource cost of the probe and the sensing action strategy, where lambda is basically how much resource cost hurts fitness.
Get the most useful information for survival and reproduction without spending too much energy doing it.
Precisely. It's a biological budget.
Yeah.
Information is the currency you need to buy fitness, but it costs metabolic energy.
That makes intuitive sense. It's like any budget decision.
It is. And we can look at this optimization in a couple of powerful ways. One is through value of information decomposition. How much does sensing actually improve my expected utility compared to the cost of that sensing? You only sense if the value exceeds the cost.
Makes sense.
Another very influential view comes from rate distortion theory, or the information bottleneck principle.
Okay.
The idea here is that the organism doesn't need all the information about its environment. It only needs to preserve just enough information about the aspects that are relevant to its tasks, finding food, avoiding predators, to achieve a desired level of performance, distortion D, while ruthlessly minimizing the amount of information it processes, rate R, and thus the resource cost, C.
Squeeze the most relevant info through the narrowest, cheapest bottleneck.
Exactly. Compress the world down to its essentials for your survival. And there's an elegant mathematical condition that sums this up, the marginal addition, which says, an organism should keep investing resources in sensing, making P better or sampling more, right up to the point where the marginal fitness benefit of gaining that next little bit of information, DDR-UR, exactly equals the marginal cost of acquiring it, DDR-CR.
So stop investing when the cost of the next bit of info outweighs its benefit.
Precisely. If it costs more energy to see slightly clearer than the survival benefit you get from seeing slightly clearer, don't do it. Stick with the blurrier, cheaper reality.
This principle seems like it would be everywhere in biology. Can we see concrete examples? How does this actively shape what's real for different organisms?
Absolutely. Let's start close to home.
Yeah.
Our own retina and vision.
Okay.
Your retina isn't just a passive camera sensor recording raw photons. It's an incredibly sophisticated preprocessor. It actively encodes things like edges, contrast, motion.
Why? Why not just send the raw data?
Because sending the raw photon data for millions of receptors 60 times a second would be metabolically insane. The optic nerve would need to be huge, the energy cost prohibitive.
So it compresses the data.
Massively. It performs an optimization, maximizing the useful visual information, channel capacity. It can transmit to the brain under severe metabolic cost, C, and wiring bandwidth constraints. It throws away redundant information, focuses on changes and boundaries.
So our reality is already pre-filtered by the retina's budget.
Absolutely. And this means organisms in different environments evolve different retinal optimizations. Think of deep-sea fish living in perpetual dimness.
Yeah.
Their visual systems are often tuned for extreme sensitivity, pooling signals over time and space, giving very low spatial resolution. They see a blurry, slow-motion world compared to us.
Because that's what's metabolically efficient and useful for detecting faint shapes in the dark.
Exactly. The physical light L might be the same down there, but their perceived visual reality, like fish, is fundamentally different from ours, left human, due to different resource constraints and evolutionary pressures. They aren't missing out on our reality. They have their own optimized reality.
Wow. Okay, what about other senses? Bats.
Bats and echolocation are a classic example. Their sonar system, producing loud ultrasonic calls and processing the complex echoes, is energetically very expensive.
I bet.
So the whole system is meticulously optimized. The frequencies they use, the timing of calls, the neural processing, it's all tuned to a bandwidth and energy sweet spot that maximizes useful information about prey, obstacles, textures, relative motion, using Doppler shifts, while minimizing that huge energy cost. C.
So they see the world in echoes and time delays.
That is their primary reality.
Yeah.
They discover and rely on acoustic features. They likely don't perceive silence like we do. Their world is this rich, dynamic tapestry of echoes, a complex acoustic landscape shaped by their probe PBAT and its associated costs and benefits. Their brain built a reality tuned to sound.
It's like acoustic vision.
Amazing. What about inside our bodies, the immune system?
Fascinating case. Think about the sheer diversity of immune cells, the lymphocyte repertoire. Your body maintains millions, maybe billions, of unique clones, each ready to recognize a specific potential pathogen antigen.
That sounds expensive to maintain. Incredibly expensive. In terms of protein synthesis, cellular maintenance, energy. So the size and diversity of this repertoire, immune, is a constant balancing act. It's optimizing coverage, being able to recognize a vast range of potential threats against the severe metabolic cost, C.
So the definition of self versus non-self depends on this budget.
In a very real sense, yes. What your immune system can reliably detect as non-self, ISY, depends on its investment in the diversity of its sensors, lymphocyte clones. In an environment with high pathogen load, evolution might favor investing more in a broader, more costly repertoire, fundamentally shaping the effective immunological reality what counts as a threat.
So even our health is based on resource-constrained reality. What about simpler organisms? Bacteria doing chemotaxis?
Tiny bacteria navigating chemical gradients swimming towards food away from toxins. Their perception is incredibly limited. By fundamental physics noise, Brownian motion, messing with gradient detection, and by their minuscule receptor budget, M, they simply don't have enough receptors or processing power to sense fine-grained or rapidly changing chemical concentrations.
So they only see the big picture.
They can generally only reliably sense ISY, low-frequency sustained gradients, small, fast fluctuations in chemical signals, which are physically present, L, are essentially invisible, irrelevant to their survival, and thus not part of their operational reality, left to be bacteria. They literally cannot see them because it's too costly or noisy.
This framework even gives a new perspective on perceptual illusions, doesn't it?
Yes, a really powerful one. We often think of illusions like optical illusions as our brain making mistakes, being fooled.
Right, like it's lying to us.
But this resource-constrained view suggests something different. Illusions might actually be the result of rational prediction mechanisms that are highly optimized for efficiency under cost constraints.
See, how does that work?
Your brain builds internal models, priors, based on past experience about how the world usually works. These models are shortcuts, efficient ways to interpret ambiguous sensory input quickly and cheaply. When a stimulus is unusual or ambiguous, the brain makes its best guess based on these priors and the noisy data, why. Sometimes this efficient best guess doesn't match the underlying reality, resulting in what we call an illusion.
So the brain isn't lying, it's being efficient, making a rational bet based on limited data and priors.
Exactly. It's using a compressed, resource-saving model of reality, and illusions are often predictable consequences of that optimal strategy, especially when priors mismatch the stimulus. Your perception is optimized for fitness, not necessarily for veridicality in all situations.
That makes illusions seem less like errors and more like features of an efficient system. What about groups? Collective or social sensing?
That's where it gets really interesting. Think of a school of fish moving as one, or an ant colony's complex foraging patterns.
Yeah, mesmerizing.
Individual organisms, like a single ant or fish, have severe sensory limitations, individual. But by pooling their noisy, limited sensory data, and coordinating their actions through simple rules or communication,
They achieve more together.
dramatically more. They collectively expand their effective channel capacity, see collectives individual, far beyond what any individual could manage alone. The group acts like a distributed super-observer, P collective.
So the colony or school perceives things individuals can't.
Yes. Colony-level laws or perceptions emerge, like finding the optimal food source, navigating complex terrain, achieving consensus that are based on pooled resources and information processing. The collective reality transcends individual limitations.
It seems biology is optimizing these resources not just moment to moment, but across different timescales too.
Absolutely crucial point. It's happening across multiple nested timescales. Immediate milliseconds.
Yeah.
This is where things like attention and active sensing come in. Your brain rapidly allocates its limited sampling effort. Your eyes make quick movements, saccades, to focus high-resolution vision on important areas. You sniff actively to analyze a scent. You're dynamically allocating P&M in real time.
Okay, short-term adjustments.
On to genetic learning. Days, years. Over longer periods, neuroplasticity tunes the filters and representations themselves. Sensory maps in your brain reorganize based on experience. Synaptic weights adjust. Your internal model, P itself in a way, adapts to the statistics of your specific environment.
Learning from experience to sense better?
Evolutionary generations. Over the longest timescale, the very sensor morphology, like eye design, and the fundamental metabolic budget allocated to sensory processing co-evolve with the environment's statistical properties, like unpredictability and the fitness landscape.
So the hardware itself evolves based on the long-term cost-benefit analysis.
Exactly. This nested optimization, fast attention, slower learning, very slow evolution makes incredible sense. It explains why organisms in highly variable, unpredictable environments tend to invest more evolutionary capital in larger brains, more flexible sensory systems, and greater learning capacity, while those in stable niches might rely more on cheaper, efficient, hardwired responses. It's a multi-layered strategy for building a cost-effective reality.
This resource lens is incredibly powerful. It seems to explain so much.
It really does.
Like why perceptual illusions are stable and predictable, they're features of an optimal resource-limited system. Why some scientific facts took centuries to discover human resource limits. Our collective P&M weren't sufficient until technology extended them.
Precisely. Or why parasites are so insidious they don't just steal nutrients. They often subtly manipulate the host's sensory processing or behavior, effectively hijacking their resource allocation and altering their perceived reality for the parasite's benefit.
And critically, why tools and technology constantly shift our own ontology, our own sense of what's real.
Yes. Every new instrument, from the microscope to the particle accelerator to the internet, extends our collective human probes, humanity. It increases our effective M&C, reduces effective size, allowing us to resolve features of L that were previously below our detection threshold. Technology literally moves us across that phase diagram, revealing new aspects of reality, changing what exists for us.
It's a truly comprehensive and unifying framework.
And importantly, this resource-centric picture isn't just a neat story we tell ourselves. It's being robustly validated by a growing mountain of empirical evidence from diverse scientific fields.
Okay, so where are we seeing this in action?
We see strong evidence for species-specific perception arising directly from evolutionary optimization in different environmental contexts. Studies consistently show, for example, that the amount an organism invests in sensory apparatus brain regions, receptor density, metabolic cost, correlates directly with things like its life history strategy, fast versus slow reproduction, and the measured volatility or unpredictability of its ecological niche.
So animals in chaotic environments literally invest more in seeing clearly.
Or at least in seeing the relevant things clearly for their survival. It's not just about seeing less if you're in a stable niche. It's about evolving a sensory system, P, that's optimally tuned cost-effectively to the specific information, S, that matters for your fitness in your environment. So different species, even side by side, actively perceive differently because their optimal P is different. It's optimization, not just limitation.
Got it. What about the collective aspect?
Collective sensing provides powerful examples, research on social insects, fish schools, bird flocks. It clearly demonstrates how pooling resources dramatically expands the group's effective channel capacity. It's collective.
The whole is greater than the sum of its parts.
Informationally, yes. The collective intelligence allows the group to sense faint gradients, map vast territories, make complex consensus decisions, infer environmental features. S, that no single individual could reliably detect, ISY for individuals, but ISY collective, for the group. It's a direct empirical demonstration of resource pooling shaping perceived reality.
And technology.
And technology, acting as a prosthesis, is undeniable. Every major scientific instrument extends our human probes. Human. Think Hubble showing us distant galaxies, LHC revealing fundamental particles, fMRI mapping brain activity. These tools don't just show us more of the same stuff. They fundamentally alter our reach, pushing back the boundaries of what's detectable. They shift our placement on that phase diagram, allowing us to resolve previously hidden spectral features of reality, bringing fundamentally new phenomena into our observable, effective universe.
It literally changes what is real for us. Okay, so this brings us back to that sort of metaphorical debate we set up between Maya, the staunch materialist physicist, and Leela, the resource-optimized biologist. Given all this evidence, what are their specific, testable predictions now?
Right, let's make it concrete. Maya's predictions matter first. If reality L is truly objective and observer-independent, then she predicts that all organisms evolving in the same physical environment should ultimately converge on perceiving the same fundamental spectral features of that environment. Evolution should find the single best way to see the objective truth, constrained only by universal physics.
Any differences are just temporary imperfections.
Exactly. And she'd predict that technological extension of our senses, PP tech, should universally reveal the same underlying physics, L, regardless of the specific technology used. Better tech just removes more noise, revealing the same objective truth underneath.
Okay. And Leela's predictions, resource optimized, what does she say?
Leela makes strikingly different predictions. She predicts that organisms living in more unpredictable, complex, or information-rich niches will, out of necessity, invest significantly more resources. M, in sensory capacity, more receptors, bigger sensory brain areas, higher metabolic costs for sensing. C.
Invest more when the world is harder to predict.
Yes, and crucially, she claims that these resource constraints, M, Pachuri, interacting with the niche demands, will fundamentally create species-specific, effective realities. Left species. What is real and perceptually salient for a bat echolocating is genuinely, irreducibly different from what is real for a human visually navigating, even if they share the same forest. Their operational worlds are truly distinct, optimized for their unique cost-benefit trade-offs.
Not just different views of the same thing, but different effective things.
That's her prediction. And what about a joint prediction? Is there a way to reconcile them?
Well, the SOF itself suggests the joint phase diagram model.
Exactly. The unifying prediction is that there should be a dynamic map, a phase diagram, in the space defined by something like environmental entropy or unpredictability versus resource cost or availability. This diagram should dynamically determine which spectral features of the underlying reality L become real, salient, detectable, fitness relevant for each specific species, given its unique evolutionary history and resource budget, MSCA.
So the diagram tells you whether matter or mind probe dominates for that species in that context.
Precisely. It captures the interplay. So what does the actual scientific literature say? When we look at the data, who's right? What's the literature verdict?
The suspense.
Well, the evidence, broadly speaking, comes down strongly in favor of Leela's predictions.
Really? Resource optimization wins.
Overwhelmingly, yes. Studies across biology, neuroscience, ecology consistently show that resource constraints and environmental variability are incredibly powerful drivers shaping highly species-specific sensory realities. Left P. We see it in sensory system evolution, in neural coding strategies, in behavioral ecology.
Can you give examples?
Work like Whitaker's on cryptic genetic variation shows how populations might harbor hidden sensory potential that only gets expressed and selected for when the environment changes, demanding new information, implying realities are contingent. Studies like Edmondson et al. On neural resource allocation clearly show brains dynamically allocating more resources, blood flow, plasticity, to areas processing more unpredictable or critical sensory input, literally sculpting representation based on information value and cost. Life history theory constantly finds correlations between environmental risk and investment in information gathering. The evidence for resource-driven perception is widespread and strong.
So biology confirms reality is actively constructed based on cost-benefit. What about Maya's predictions of convergence?
Maya's predictions hold true only in specific, often limited cases. Yes, there's sometimes functional convergence, like blue-green vision evolving independently in some deep-water mammals facing similar light constraints. But it's far from universal. We see many examples of non-convergence, where species in similar environments maintain distinct perceptual worlds due to different evolutionary starting points, different secondary ecological pressures, or slightly different optimization trade-offs. Convergence is the exception, not the rule.
And the joint phase diagram model.
That model receives increasingly strong support. Dynamic resource allocation modeling in neuroscience, behavioral ecology, and even areas like active inference in AI is consistently confirming the existence of these phase-like transitions. How an organism allocates its sensory budget, PM, demonstrably changes depending on stimulus predictability, task demands, and perceived costs, leading to qualitatively different perceptual regimes. The phase diagram concept seems to capture the dynamic reality well.
So the verdict is nuanced.
It's nuanced. But the weight of evidence strongly suggests that who wins, whether reality seems fixed like L or fluid like Lef, fundamentally depends on the organism, its resources, and its context. Reality, as constructed by perception and interaction, appears highly fluid, adaptable, and profoundly resource-dependent. It's a biological process shaped by optimization, not just a passive reflection of a single pre-given truth.
Okay, so if this resource-constrained view is so compelling, so well anchored in the data, how do we push it further? How do we really nail it down? What kinds of concrete experiments could researchers do now, or observations could they make, to test these ideas even more rigorously?
That's the exciting part. This framework isn't just explanatory, it's highly predictive. It generates concrete, testable hypotheses that experimentalists can tackle.
Like what? Give us some examples.
Okay, first, we could look for strong cross-species resource information correlations.
Comparing different animals.
Exactly. The hypothesis is species that evolved and live in more unpredictable, complex, or information-rich environments should have demonstrably greater sensory channel capacity, C, per unit body mass, or maybe per unit metabolic rate, compared to species in stable, predictable environments.
How would you test that?
You'd need to compile large data sets across many species to measure things like receptor counts in eyes, ears, noses, estimate the size or energy budget, MC, of sensory brain regions, quantify their investment in information processing, then correlate these biological investments with quantitative measures of their ecological niche's entropy, predictability, or complexity. You'd predict a strong positive correlation.
So literally measure how much sensory hardware and energy they spend and see if it matches how challenging their world is. That's direct.
Very direct, though data collection is challenging. Second prediction. We should find rate distortion signatures in neural codes.
Looking inside the brain.
Yes. The framework, particularly the information bottleneck view, predicts that the way neurons encode sensory information, their firing patterns, their tuning curves, their adaptation, should match the mathematically optimal solutions for compressing information while preserving task-relevant fidelity, D.
So neurons should behave like optimal data compressors.
Exactly. You could test this by recording from sensory neurons under various conditions and then carefully fitting information bottleneck models or other rate distortion optimal models to the data. Do the observed neural codes match the predictions for optimal compression given inferred costs and benefits? If so, it's strong evidence for resource optimization shaping the neural representation of reality.
So we check if the brain's code is as efficient as the math says it should be, given the energy budget. Fascinating. What else?
We can get more causal with resource perturbation experiments.
Actually messing with the resources.
Yes, carefully and ethically, of course. For example, you could temporarily impose energy budget constraints on an animal, maybe through mild caloric restriction, or by increasing the metabolic cost of a task. Then you precisely measure changes in their sensory behavior.
What would you measure?
Things like their attention allocation. Where do they look or listen? Their exploratory behavior. Do they seek out new information? Their reliance on learned habits versus flexible responses, their perceptual thresholds.
And the prediction.
The prediction is that under tighter resource constraints, overtreases or M decreases, organisms should demonstrably shift their strategy. They should invest less in costly information-seeking sensing and exploration and rely more heavily on previously learned priors, stereotypes, and energetically cheaper behaviors. Their effective reality should become narrower, more predictable, more model-driven.
So being low on energy makes you stick to your assumptions, even if reality changes. A direct link between metabolism and perception.
That's the hypothesis.
Yeah.
Then there's comparing collective versus individual sensing.
Like the ants and fish again.
Right. Design experiments to directly quantify the information gain per unit energy cost for individuals versus groups performing the same task, like foraging or navigation.
What's the prediction?
Predict that collective strategies through resource pooling and information sharing achieve significantly higher information gain per unit energy. This would clearly demonstrate the power of pooled resources in expanding channel capacity and constructing a richer, more accurate shared reality, left to collective, that's inaccessible to individuals.
Quantifying the benefits of sociality for perception. Makes sense. Anything else?
Finally, we can use simulated evolutionary runs.
Computer simulations.
Yes. Create agent-based models where artificial agents evolve their sensory systems, sensor count, quality P, information processing strategies within simulated environments with varying levels of complexity, predictability, entropy, and metabolic costs.
Like digital evolution in a bottle.
Exactly. We would predict that the evolved sensor complexity, the channel capacity C, and the sophistication of the agent's internal models would directly correlate with the environmental unpredictability and the fitness benefits of information. We could potentially observe those phase transitions dynamically, seeing how different resource landscapes lead to the evolution of different effective realities in silico.
That would be a powerful way to see the principles in action, watching different realities emerge from the simulation based purely on resource pressures. These are all incredibly exciting avenues for future research. Hashtag tag, 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 outro. So after this really deep dive exploring matter, mind, observers, resources, let's circle all the way back to where we started. Back to that 8-year-old Sam, asking that incredibly simple yet incredibly profound question. What makes you sure that something exists at all?
Such a great question.
And apparently at the end of that whole philosophical back and forth, Sam, just listening quietly, offered his own observation. With this knowing smile, he supposedly said, so, existence is what survives the filter of resources, whether brain, body, or cosmos.
Wow. Out of the mouths of babes. That's actually brilliant.
Doesn't it?
That simple statement just perfectly encapsulates the core takeaway from this entire deep dive, doesn't it? It's elegant, concise, incredibly insightful.
It really ties it all together.
It does, because matter, L, sets the hard walls. It provides the fundamental constraints, the rules, the spectrum. Mind paints the pictures. Observers, biological, technological, select and construct effective descriptions, less based on their coupling, their needs, their priors. But ultimately, and this is the crucial synthesis from the SOF, resources, MCC, decide the game.
Resources are the filter.
They're the filter, the available energy, sensors, bandwidth, the noise floor. These are the fundamental arbiters of what becomes real, what features as actually survive that filter for any given observer.
Is there a mathematical slogan for that?
If you want the crisp mathematical slogan, it's basically this. Organisms, or observers, choose an optimal probe P by solving P argmax PP. And that chosen probe P then defines their effective reality, RP. Right. That single optimization equation summarizes the entire resource layer. The optimal probe you can afford, driven by fitness, defines your operational reality.
P defines RP. The reality you get is the one shaped by the best probe you can afford.
That's the essence of it.
This whole perspective, it's truly mind-bending, and it leaves us with a really important, maybe even slightly unsettling question to ponder, doesn't it? If your reality, the very world you perceive and interact with every single moment, is fundamentally shaped by your resources, your brain's limited energy budget, your senses' inherent limitations, the tools and information you happen to have access to, the collective knowledge you're embedded in. Then what new realities, what currently unimaginable layers of existence L might be revealed as our technology P continues to grant us ever more powerful eyes and ears and brains?
A profound question.
And maybe more personally, What aspects of your own current reality right now might just be a function of your own personal, biological, cognitive, or even societal resource constraints? What could you potentially see? What could you experience as truly real if those constraints were somehow lifted?
It certainly makes you think about the boundaries of our own perception, doesn't it?
It really does. Something profound to mull over until our next deep dive.